Welcome, everybody. Thanks for being here. So, yeah, I'm Elena Losero. I'm currently working at EPFL, but this work was done in collaboration with my previous affiliation, which was INRIM in Torino, in the quantum optics group led by Marco Genovese, and with Stefano Pirandola in York. So before going into the details of quantum reading, just let me tell you a few words about the two-mode squeeze state of light, because it will play an important role in the next. So what is important for us is that this quantum state of light has this representation here in the Fock basis. And in particular, the main feature that we will exploit is the fact that it presents perfect quantum correlation between the two modes. We can also extend this state of light to the multi-mode situation. Therefore, we can consider the so-called multi-mode squeeze vacuum state of light, which also presents perfect quantum correlation between the signal and the idler mode. This is particularly important because this state of light can be easily implemented experimentally, pumping a nonlinear crystal with a laser. And what we obtain are two down-converted photons, which respect both momentum and energy conservation. And if we focus at the degenerate condition, the perfect momentum conservation will be translated into perfect position conservation at the detector plane. So at least in the ideal case, if we have 2 point-like detector in X and minus X, they would detect exactly the same number of photons. So now let's move to the quantum reading scheme. The idea of quantum reading is to infer the value of a bit of information which is stored in a certain memory cell. And in particular, in our scenario, we consider as a memory cell a lossy channel who can have two different values, tau 0 and tau 1, which will correspond to our 2 bits, 0 and 1. To recover this bit of information, we have a certain transmitter, which produces a certain quantum state, a certain state of light, ρ, which has m signal modes and L idler modes. The signal modes goes to the memory cell, interact with it, and then goes to the receiver, while the idler mode goes directly to the receiver. At the receiver, we can perform a certain measurement, and after the measurement, we will be able to recover our bit of information. Of course, this procedure will be affected by a certain error, PR, and the question that we can ask ourselves is, what is the lowest bound for this error probability? In general, this question is not easy to answer because it involves a double optimization problem. But anyway, what we can do is to try to restrict our research to classical transmitter. And in this case was studied theoretically in this paper in 2011. And from this theoretical study, it comes out that for classical transmitter, there is a lower bound for the error probability that we call as Elstrom bound, which has this expression here. What is even more interesting is that this bound can be surpassed if we use quantum states of light. And in particular, if you use the quantum state of light I presented you at the beginning, we can do better than what we can do with classical states. The figure of merit that the author introduced here is called gain and is written in terms of the binary Shannon entropy. And the important thing is that this gain has a maximum value of 1, which corresponds to the case where quantum strategy can recover the bit of information while the classical strategy completely fails. And every time that we have a gain which is bigger than 1, we have a quantum advantage. And here they show that this is the case while using the two-mode squeeze vacuum state. Even if they don't propose any concrete strategy, neither a precise receiver. So it's something very theoretical, but not experimentally realizable. What we did in our work was really to move this theoretical study from the ideal theoretical world to the real world. And in particular, what we proposed was an explicit quantum reading strategy with photon counting. We studied then the role of losses which are unavoidable in experiment, and then we experimentally implement the protocol demonstrating a quantum advantage. So for the quantum, as a quantum reading strategy, we consider a photon counting receiver. A photon counting receiver is basically probably the simplest receiver that you can imagine. So it's a receiver whose output is simply the number of photons detected in the signal and in the idler, respectively. From this number, this couple of numbers, we should infer the value of the bit of information. To model this situation here, what we did was to start from the photon distribution at the transmitter, and then to compute the photon distribution after the interaction with the lossy channel tau, simply combining the initial distribution with a binomial distribution of parameter tau. So our strategy consists in a photon counting measurement followed by a maximum likelihood decision. So the idea is simply the following one. We decide the value of tau 0 or tau 1, choosing the value which maximizes the probability of having tau u, given the fact that the measurement outcome was ns and I. And in the same theoretical framework, we can also easily evaluate the error probability in this way, so considering the other probability. We propose this strategy, but it's also important to understand if this is somehow useful, a great strategy, in the sense that we want to see if this photon counting strategy is very, very far from the Elstrom bound, or if it's somehow comparable. So in this plot here, we plot exactly the error probability versus the number of photons in the signal for the photon counting strategy and the Elstrom bound. And what we can see is that the photon counting strategy is a reasonable strategy, it's a good one, because it's not too far from the Elstrom bound, and it's really easy to be implemented. This is the curve obtained for a classical transmitter. And the classical transmitter is simply a coherent beam, for example, with n photons in the signal. While these are the results obtained for a quantum transmitter, and in particular for a two-mode squeeze vacuum state. On this side, so on the left, we have the quantum gain respect the classical transmitter plus photon counting strategy, while on this side here we have the quantum gain versus the Elstrom bound. And you can see that in both cases we have big regions where the quantum gain is bigger than 0 and very close to 1. So this means that this strategy really improves the performances of the protocol with respect to the classical case. But till now, everything was ideal. So these plots here were obtained with an efficiency equal to 1. But this is not the case in the real experiment. So what we did next was to introduce, to model also the role of the losses. So in an optical setup, there are losses, for example, in the optical components. There is the quantum efficiency of the detector. So we can put together all these losses into a coefficient that we call detection efficiency. And that what we can say is that we will have a composite pure loss channel whose transmittance is simply the product of the memory cell loss transmission and the detection efficiency. It is important to note that losses have a different affect in a different way classical states and quantum states, because from the classical side, the only role of losses is to decrease the mean number of photons in the signal, basically, and therefore to increase the shot noise. While in the quantum state, they also decrease the level of correlation. Therefore, what we expect is that in presence of losses, the gain will be lower than in the ideal case. And this is actually what we found. So these are the same graph I presented you before. So the gain respect to the classical strategy with photon counting and the Elstrom bound in presence of around 20% of losses, which was what we had in our experiment. So what we can see here is that there are again, there is again a quantum advantage. So there are regions where this gain is higher than 0, but the absolute values are much lower than before. But anyway, they are significantly different from 0. So now let's move to the experimental implementation of this protocol. So this was the quantum scheme I presented you before. Now, for realizing the experiment and validate the model I presented you, what we did was to consider as a transmitter a multi-mode two-mode squeeze vacuum source. So simply SPDC in a BBO crystal. Then what we used as a memory cell was a coated glass slide with a deposition of variable transmittance in order to vary the parameter tau 0 and explore a different range of our model, of our parameters. While for the receiver, we used a CCD camera and photon counting strategy, followed by a maximum likelihood decision. So this is a slide which should help to understand, at least from an intuitive point of view, why this strategy works. In this plot here, I reported the photon number distribution for signal and idler. And what we can, for the two different transmittance, tau 0 and tau 1, which are two levels of, which encodes the 2 bits of our channel, of our bit. And what we can see is that due to quantum correlation, these distributions has a squeeze shape, and therefore they can be easily distinguished compared to not squeezed distribution. While on in the bottom side, in the bottom plot, you can see what the information that we can have while having access only to one of the two channels, which corresponds to the classical case. And we can appreciate that in this bottom plot, the two distributions are much more overlapped compared to the first plot. So this is why the quantum resource, it is why if quantum resources are exploited in the correct way, we can do better than in the classical case. So this is my last slide, basically, where we summarize the results obtained. So these are the red and blue curves are the theoretical curves obtained from our model using the parameter of the experiment that we had. And they represent the gain respect to the classical strategy and the Elstrom bound. The dots are the experimental point, and you can see that the dots are, are well into the curves, but even more importantly, what we can see from here is that we demonstrate a significant quantum advantage, both respect to the best classical strategy and the Elstrom bound, which is what the best obtainable from the theoretical point of view, if limited to classical resources. So in summary, what we did was to propose a practical receiver with performance close to optimality based on photon counting and maximum likelihood decision. Then we investigate the realistic scenario where losses are present. And finally, we experimentally implement the quantum reading scheme using multi-mode squeeze vacuum states produced by SPDC and a high efficiency CCD camera, demonstrating a significant quantum advantage. And yeah, I think that's all, and I thank you all for your attention.
Thanks, Elena. It's a very nice talk. Other questions? Yep, there's a question.
Hello, thank you. So maybe I missed that, but what was the level of squeezing in your two-mode squeezed vacuum, and how things depend on the level of squeezing?
Okay, yes. Yeah, I didn't report, I think, any plot, any plot for that.
I somehow would expect the plots, your 2D plots would depend on
Oh, of course, higher is the level of squeezing, better would be the advantage. And this is basically, I mean, the level of squeezing basically depends on losses in our case. So higher are the losses, lower is this squeezing. And in particular, what we can, the figure of merit that is really important here is the so-called noise reduction factor, which is related to squeezing, but it's not it's just a matter of definition probably. And the noise reduction factor is defined as 1 minus eta, where eta are the detection efficiency of the setup and of the, yeah. So in our case, this level is 0.2 more or less. So this noise reduction factor in this case is 0.8. And closer we are to 1, better is the correlation between signal and idler, and therefore better will be the quantum advantage.
And what's the detection efficiency of your camera?
Sorry?
What's the detection efficiency of your camera? I suppose that's the main source of loss in your
No, the detection efficiency of the camera was good. I think it was at the frequency we were using, which was 810 nanometer, which was the detection efficiency was higher than 0.95, something like that.
So the main source of loss then?
The main source of loss is the optical setup itself. So lenses filter, the interferential filter in particular was quite crucial because in our case was not a very good quality one and introduced many losses.
Okay.
Yeah.
Wonderful.
So I understand that tau1 was always 1 in your
this
plots.
Yeah, in this case here,
And
what
tau0 was kind of close to 1.
yes.
So you had to have very low losses in your memory. Yes, I mean this had to be almost perfect transmission. Yes? So I wonder what's kind of optimal choice. Yes, because I guess that now when you want to perform better with higher squeezing, you probably again should choose this tau0 closer to 1 and so on. No?
Okay. Well, the model is, in the model we don't need really to have tau1 equal to 1, so we can choose in our model the value that we want. So but then if we want to, we focus on tau1 equal to 1 because this was, we wanted to find a range of parameters where we could really see a quantum advantage. And the idea is that you can have a quantum advantage is shot noise is your limiting factor. So if you have tau0 and tau1, which are very different each other, shot noise is basically not a problem, and therefore is almost useless to go into the to use quantum resources. So the fact that tau0 is so close to 1 is due to the fact that is when the two values are very close that shot noise becomes important and therefore limits your classical distinguishability between the two levels.
But do you have a now practical argument why somebody would like the memory like this? I'm not just like, transmit everything, absorb everything.
Yes, okay. Okay, maybe it's more related to to absorption measurement rather than this particular application. If I think to absorption measurement, what I can say, okay, is that, for example, if we want to estimate concentration of something through absorption measurement, in that case, it's relevant to distinguish maybe two different levels of concentration, which are very close each other and which are also very, very low.
But then usually it will be like continuous parameter you would like to estimate.
Exactly.
And it will not be this discrimination problem.
Yes.
And then things will change.
But
okay.
Yeah, you can also have presence of absence of maybe you want to distinguish between two different levels.
Okay. Okay, thank you.
Yes.
Cannot see any other questions. I'll allow myself a quick one if I can. On your last result?
Yes. Wait.
I'm just curious.
Yes, of course. I have to answer.
So you showed two results, two plots that look quite similar to each other. So I was wondering if they are so similar because the n is of the same order of magnitude, and then how would it change if you really change the number of photons.
Okay, yeah. The difference between these two plots is in the number of photons in the signal. Yes, this is true. What we can observe here is that, okay. So the change is, there are two different changes that we should observe. One is that increasing the number of photons, what we observe is that the absolute value, the maximum quantum advantage that we observe is higher, is a bit higher, but the region where we observe it is a bit smaller. And this is a trend that we observe. Now I reported these two values, which are quite similar, but yeah, maybe it wasn't the best choice possible, because we tried also in a bigger range, and this trend is confirmed. So, and you can see it also here. So what we have is that increasing the number of photons, the maximum gain moves toward greater tau zero. And this is again due to the fact that I was explaining before, that if we have higher number of photons, it means that the shot noise is lower, and therefore to observe a quantum advantage we need to go to a regime where classically is very difficult to distinguish between tau zero and tau 1. So this is why increasing the number of photons in the signal, the maximum quantum advantages goes toward higher value of tau zero.
Okay, thanks a lot. So we will move to the next speaker. Thank you very much.
You're welcome.